yeah, I'm gonna record this and put it online just in case anybody wants to look back on it, or if someone joins halfway through and missed the first part, they can go online. Uh, YouTube, I think it's at MathPond. So youtube.com/at MathPond. There we got Kyler. Yeah, so I was just talking about. This is a little bit of my research, my PhD thesis research, and I've been still working in developing like a more general solution. And I have basically come up with a formula, and I just need to prove it. So yeah, let me explain a little bit of the background first, and then we'll kind of like work into Operads. I kind of want to motivate it first, so let's see. Is all the lighting good? Yeah, the lighting looks pretty good. So yeah, I put two links in the chat. The first link is a paper from my advisor and one of his co-authors. So that's this first paper. This is a graph homology and graph configuration spaces. And this is work by Vladimir Baranovsky. And Radmila Sazdonovic. How do I spell this? Yeah. Okay. So that's the first link. The archive link there is for this paper, right? Let me just switch the color. Right, so I think this is a brilliant paper, very, very well written. Talks about if you're given a graph. So I guess the original motivation would be computing the homology of configuration spaces. So in physics, you have like some manifold. Let's say it's like a donut. I was terrible at these. How do I draw a donut? All right, so it's got like some holes. How do we do a donut? I'm so bad at these. Donut. Right, and so configuration spaces in physics asks the question of, if I take a bunch of points on a manifold and I look at the space of all possible configurations of those points, so like I can move this point around to somewhere else, I can move this point somewhere else. I could also have these points sort of like wrap around each other in some sense. If you think up to homotopy, you can move them around, they can wrap around each other and sort of knot around each other in space. So I guess the fundamental motivating question is, like, given a manifold or some simplicial set, what is the structure of this configuration space on that manifold? So where I take multiple points and I allow them to move around, that's kind of like the motivation here. So motivation, what is homology of configuration spaces? And from some other work, it seems likely that the question involves something to do with the algebra on the original manifold itself, which you could imagine would be the case, that the configuration space on the manifold, the homology of that is somehow related to the homology of the manifold itself, right? That doesn't seem too surprising, right? But it turns out computing this is not very easy. It's not like a trivial process. So just because you know everything about the manifold, like up to homotopy, maybe you know the whole cohomology algebra, you know the product on it, but it's not exactly trivial to go from that to now the homology of the configuration space. So this is basically the motivation that this paper is kind of working out. So there's a whole previous work that I don't want to go too far into, but there's this Bendersky-Gittler complex that is basically this giant complex, which is abstract, which is supposed to compute this configuration space. So we have, I'll just write down the name. I don't want to go into the whole, I could talk a little bit about the way the complex is structured, but I think from stuff I'm about to do in a second, it's not going to be too important. But let me just write down the name. So I think it's Bendersky-Gittler complex. Right, so this is some homological complex that is supposed to compute this configuration space. Configuration space. Right. Yeah, they're not allowed to be the same point. Yeah, so I believe, yeah, let me be a little bit more specific. Yeah, so we, there's different notions of the configuration space. You can, yeah, if you let the points overlap, then you just have m to the n, right? Then you're just talking about n points on m. So yeah, you specifically want to make sure that the points are not allowed to overlap. So they can they can wrap around each other, but they can never intersect. But there's actually a generalization in a second I'm about to talk about where some of the points are allowed to intersect and some of them are not allowed to intersect. So, but yeah, it's a good question. Do I need to say more about that? Are you still confused? So I think you're right. Maybe you want to remove the diagonals. Yeah. So we're going to be basically, yeah. So this complex is built from removing those diagonals, essentially. Like, you basically break it into like a pairwise thing where you look at each pair of points individually, and then you have a diagonal coming from that. And when you look in the dual space, it becomes a product. So essentially, this complex, actually, yeah, I'm going a little bit too quick here, but yeah, let me slow down a little bit, and all this will make a little bit more sense in a second. So this is just like the motivation. Let's keep it a little informal. The motivation is we want to compute these configuration spaces, and Kyler is correct. I believe we want to be careful about the way the points can overlap, or whether they can overlap or can't. But yeah, this is basically the idea. Oh, and Kyler, if you got here late, this is the first paper in the first link, the archive paper. Right, so on our mission to compute this homology, there's a related complex that computes something similar that I guess mathematicians at some point realized that these two things were related, but there's this, I believe it's called the chromatic, well, there's this chromatic polynomial for a graph, but there's also a homological version, which is the chromatic, I forget the exact name, I think it's chromatic graph cohomology, I want to say. And there's this construction where like you have the graph cohomology, then you take this like graded Euler characteristic and you recover the polynomial. So the polynomial is kind of like a special case of this graphical homology. And the way you compute this is similarly to like we were just talking about with the diagonals. When you're talking about, so there's a product on C star of M. So the N here just stands for normalized. So these are normalized cochains on some like manifold or simplicial set or something. And this is just the normal product, which comes from the pullback of the diagonal. So you take like some sigma, you send it backwards, you get sigma comma sigma, or sigma tensor. Well, there's like sigma 1 tensor sigma 2. You split it using the Alexander-Whitney map, and then you like apply, you have two cochains, so you apply like the first one to sigma 1, you apply the second one to sigma 2. Because these are the duals, so basically you want to map backwards because that gives you the product going the other way. Right, so there's basically this giant complex which is built out of a bunch of these cochain things. And the differentials come from the pullback of these diagonal maps, like Kyler was pointing out, that you're throwing out these diagonals for the configuration space. So it might be believable that this has something to do with this multiplication map, where you have this diagonal, then you apply Alexander-Whitney map, and you get this. So this is the cochain product. This basically defines a product on cochains. Where so let me kind of draw this out. Basically, you're taking these like triangles, and you're splitting the triangle into like the ith first face and then some n minus ith back face, and you're applying, you have some function on these things, and you're just applying the function to the first ith face and then the n minus ith face, and it's actually like a sum over a bunch of these. So I'm being kind of informal here, but you can look you could look this up if you haven't seen it before. There's just, there's a product on cochains. It's given by the pullback of this diagonal map, Alexander-Whitney map, and that defines this product. Yes, dual spaces. I don't know what I'm watching, but I chill. Yeah. So essentially, the product and just the cohomology in general gives you information about the space. They're like invariants of the space. So like we've been doing linear algebra in the regular stuff. There's the dimension of a vector space. So some of the easiest invariants to compute in cohomology is you have, maybe your ring is a field here that you're dealing with. So all of your spaces are modules, and then you could just ask what's the dimension of these various spaces. So you have like the degree 1 stuff, the degree 2 stuff, etc. Also, this product is also an invariant. So if you have a space M or a simplicial set, and you're looking at the cochains on it, this product, like up to isomorphism, defines is an invariant for the space. So like if you have some product structure on 1M, you have a different space, and you can show that the products are different, then you can show that the spaces are different. So a big thing in algebraic topology is, given two different spaces, how do you actually show that they're either the same space or that they're different? And it's not very easy in general. So we come up with these tools that help us to do that, and one of these tools is we have cohomology modules or vector spaces, and in this case, for cohomology, there's also this product, which is another invariant. And there's actually like higher and higher invariants. So you have the product, there's this notion of like, it's not commutative. So I'll go over this in a second. Let me slow down a little bit. Are there any questions about this? So I know some of you probably don't know what I'm talking about, but the big picture idea here is just we have some space, some notion of like a space, so it could be like a donut, or it could be a two-hole donut, or in any dimensional space. And this structure here is telling us some information about that space. So this is basically, you could think of these as like a bunch of vector spaces, and the dimensions of those vector spaces might tell us some information about the space. So like how many holes does the space have, for instance, could be some information we could get out of here. And like I was saying, also the product structure tells us something about the space as well. But it doesn't tell us like everything about the space. So it's actually possible that two different spaces have all the same vector spaces here, have the same product up to isomorphism, but actually they're not the same space up to homotopy. So it turns out you need more information than just this product. You need a bunch of like higher products, and that's where the Operads stuff starts to come in. So you want some some kind of higher product structure on some cohomology theory that is homotopy invariant. Yeah, exactly. So it turns out that, like I was saying, that this product isn't quite enough. That you need a bunch of higher products. So it turns out that this product is actually not commutative, but it's very close to being commutative in the sense that there's actually a homotopy that fixes the commutativity in some sense. So there's a homotopy between like multiplying in one direction or flipping the order and multiplying the other way. They're not like exactly equal to each other, but they're extremely close. In fact, they're so close that once you reduce to cohomology, there's no difference anymore. So it's very close to commutative. In fact, yeah, when you reduce this product, so this product you can project onto the cohomology, and in cohomology it is commutative. So it starts out not commutative, but then you project to the cohomology, and then it becomes commutative. So it's like almost commutative. It's very close to commutative, and we call this structure. So this is not commutative. But it does have a structure which we call an E infinity structure. So it's an E infinity algebra structure. Which just essentially means that I can take any number of these and I can multiply them in any order. And I might get different things, but there's some homotopy that like repairs all of the differences between all the different ways I can multiply. So they're not actually equal to each other, but they're homotopic. Okay, so that's kind of like, I don't want to say this is like the original motivation for Operads, but it's, well, the original motivation for Operads was infinite loop spaces. And the fact that this is an E infinity algebra says something like it's behaving somewhat like an infinite loop space, but like in an algebra sense. So yeah, I'm being pretty informal here, but yeah, somehow this E infinity structure is related to infinite loop spaces as well. Okay, so let me go back to the paper. Or actually, let me show you how to define this. So this graph cohomology stuff, this makes sense as long as you're dealing with a commutative algebra. So we actually can't use the cochains themselves because, like we just said, they're not commutative. But for certain, so there's actually, like, I'm leaving this out, but there's cochains with coefficients in some ring. And depending on this ring, you have different stuff going on, different results kind of apply. So basically, if the ring is just the integers, then there's certain things that are known about this cochain the relationship between the cochains and the cohomology ring itself. And if it's like the rational numbers or the real numbers, then there's some sort of relationship. Actually, let me write it out, because without writing it, it's a little confusing. But all right. So any questions? Yeah, actually, yeah. So let me just point out. So example 6 in the paper is very important. And so basically, the thing that we want to compute, that will compute this thing, everything works out if we have commutativity. And in certain cases, we can actually use a replacement for the thing I was writing before that wasn't commutative. We can replace it with something that is commutative. And that's the case like if the ring that you're working over is the rational numbers. So if you're working with cochains over with coefficients in a field of characteristic 0, like the rational numbers or the real numbers, then we can actually replace the non-commutative algebra that we were working with something commutative, and then everything's fine. So this is kind of like the work of the paper, the Baranowski paper I was just talking about. So if R is Q, then we can replace this algebra, which is not commutative, with something called, I think it's called the Sullivan cochains. And this Sullivan cochains algebra is commutative. And it turns out that there's a quasi-isomorphism between these two. And it's like so, for linear algebra, we have a notion of an isomorphism between vector spaces. In homotopical algebra, you don't necessarily require that two structures are exactly equal or exactly isomorphic. They can be like isomorphic up to homotopy. So here, the correct statement, the relationship between these two, this algebra and these Sullivan cochains, which is commutative, is that there's a quasi-isomorphism between them. So I'll write it as like quasi-isomorphism, and that means that, like I was saying, they're not, the structures are not exactly isomorphic, but if you kind of reduce everything down to cohomology, then it is an isomorphism. So it's some sort of function between the two that is not necessarily an isomorphism, but once I reduce everything to cohomology, it becomes an isomorphism. So yeah, so this thing is not commutative. This Sullivan cochain algebra is a replacement for it that is commutative. And then you can run this whole then you can run this whole process of creating this graph cohomology complex, and because everything's commutative, everything works out and the differential exists. So really the only problem is if we can't replace this with something commutative. So when R is the real numbers, you also have a replacement. So if R is the real numbers, then you have this de Rham differential forms complex. So you have like all of the 1 forms, 2 forms, 3 forms, n forms. De Rham forms complex. Yeah. So then this complex is commutative, and you can use that as a replacement for this, and then you can do everything with that, and that works out. Oh yeah, sorry about the ads. I tried to turn the ads off, but then it says it lowers the already tiny amount that I'm making to like even less. So I don't know, it's crazy. But yeah, if there's any ads going on, just let me know and I'll slow down so the ads can stop. So you want some sort of higher product? There's homotopian variant. Quasi-isomorphism preserves the product structure right on each complex. What do you mean by that exactly? I mean, you can think of a quasi-isomorphism as it's an isomorphism on cohomology. So it doesn't necessarily need to preserve the structures exactly, but once you reduce everything to cohomology, it becomes an isomorphism. If that makes sense to you. Because every function between these types of cochain complexes, if you have a function between these, you can always reduce. There's always like a projection onto cohomology. So you can ask, okay, I have a map between these. If it's a quasi-isomorphism, I'll project everything to cohomology. If that's an isomorphism, that means the original map was a quasi-isomorphism. And it just essentially means that the product on this bigger space, once we reduce to the smaller space, the product is somehow still working with the homotopy in a coherent way. Yeah, thanks, Stuki. Right, so basically where I was at was we have this chromatic graph cohomology complex. It's basically defined for any algebra that's commutative, and we want to be able to use this algebra because this will compute what we want, which is the information about the configuration space. But we essentially can't use this all the time because it's not commutative, but we can replace it with something commutative if we're working over a field like Q or a field like R. But it has problems if you're working over something that's not a field like the integers, or if you're working over a field of characteristic P, so something not of characteristic 0. Then my understanding is the problem is well, first of all, yeah, this only exists over Q. So these Sullivan cochain algebra stuff only exists over Q. I don't think there's a good replacement. And I think at some point you need to, well, at least for the Massey product stuff I'm going to talk about in a second, I think you need to do some sort of like division over all permutations, and you end up like dividing by n factorial somewhere. So if you don't have rational numbers, the whole construction like breaks down or something. That's my understanding of it, at least. Basically, the hours ad free. Yeah, I'll talk to you guys about it. I didn't really know what I was doing when I set it up, honestly. So if there's a better way to do it, I mean, I'm obviously not really. I'm making like sense every hour, anyways, so it's kind of pointless. But right. So I think that's good. Any questions before I go on? So really, the whole story here is that we want to be able to replace this with something commutative, but it's only possible on the nose if like the ring is rational or real. Otherwise, if the main case we really want to be able to work with is when R is the integers, and in that case, this is not commutative, and that's essentially like the whole work that I'm dealing with. So. Yeah, when this is not commutative, what can we do? So that's like the question. Okay, and also, so in this Q and this R case, there is actually a way where you can just, so these are not the cohomology algebras themselves, but you can actually reduce everything down to cohomology, and then you have to do some like perturbation lemma thing to keep track of everything, and in the end you end up with these like, you end up with the spectral sequence, and all the higher differentials basically come from these higher Massey products. So there's like, yeah, there's this A infinity structure on here, and you can keep track of it by going down to cohomology, but then you end up with all these Massey products. So same type of story. You have like these higher products that need to keep track of everything that you messed up, essentially. Which is like a big theme here, is essentially we have these like large complexes, we map everything to some smaller complex that's easier to deal with, but then it messes up all of the computations, so we need a bunch of correction terms. And once we add in all the correction terms, then it ends up computing everything correctly like we wanted. So yeah, that's the story. So yeah, how do we deal with this when R is the integers and we can't replace it with something commutative? That's the real question. Yeah, so I'm probably gonna go for like, I guess I could go for like 2 hours, but maybe if everyone's bored or I get tired, maybe we'll end early, but right. So let me just put up the point I just said before. So one can reduce C star n mr all the way down to this cohomology ring. And use this for graph or chromatic graph homology. And this computes what we want, which is this configuration space homology. And then the big if, so it computes what we want if we add in these higher correction terms. Correction terms coming from these higher Massey products. And these Massey products are just like the remnants of the A infinity structure coming from here. So there's an A infinity structure here, which is just normal multiplication. But remember, it's not commutative. Then we can pass down to cohomology. Now it is commutative, but we can basically transfer this A infinity structure from here down to here. And this now is commutative, and we can use this to compute this graph homology complex thing. But then there's a bunch of correction terms because when we project down to here, we're sort of losing information about the product in some sense. So we need to have these higher correction terms that fix the errors. But once we add in all those extra terms, then it does actually compute what we want. The only thing is that this quasi-isomorphism, where it's actually a quasi-isomorphism of A infinity algebras, this only exists in certain cases, like what we were talking about when R is Q or R is the real numbers. So yeah, let me just repeat that. So this quasi-isomorphism here of A infinity algebras and I'm writing it as one line, but there's actually this notion where you can actually connect them with this like zigzag structure. So I'm being a little informal here, but just take my word for it. So yeah, there's only this quasi-isomorphism of A infinity structure doesn't always exist. Doesn't always exist. So it only exists in those special cases that I was talking about. Yeah, so what can we do to repair this situation when R is the integers? That's essentially where, well, even before, like once we start talking about A infinity structures, we're already talking about operads. So let me show you. I actually want to avoid the definition because I think the definition of an operad is like almost overly bulky. Like it's probably going to take me 30 minutes just to write all the stuff down. I feel like it's almost better to just see some simple examples and you could sort of like imagine in your head what this structure is, because it's really not complicated of an idea. Like an operad is just a bunch of symbols that represent operations on some algebra. So for instance, if there's only one symbol, then there's only one way to multiply in your algebra. So that's actually the simplest operad is just a point, and that's called the commutative operad. So let's just start there. Can you still have a comparison map? What do you mean a comparison map? Is there still a projection from cochains to the cohomology? Is that what you're asking? I mean, this projection always exists, right? No matter what ring you're dealing with, right? You can always project to the cohomology. It's just that this projection doesn't preserve the A infinity structure, even up to homotopy. So the projection is still a map that exists. Yeah, it's just a map of chain complexes, but it's not a quasi-isomorphism anymore, exactly, yeah. Oh, am I dropping frames? Still good? Can you guys hear me? Here, let me check. Yeah, but if you can hear me, Kyler, still, yeah, that's the correct idea. Okay, yeah, so like I was saying, yeah, this projection always exists. You can always map cochains to the cohomology by projection, but yeah, it doesn't preserve the multiplication product, even up to homotopy. Yeah, that's the problem. Oh, okay, yeah. Sorry about that. I think it's not dropping frames now, so hopefully that doesn't happen again. Right. So let's just look at a couple examples of operads. Simplest case. And so, yeah, without writing the formal definition, you want to just think of an operad as something that is a symbol that's representing some way of multiplying something. So the simplest operad is just a single point, and that's representing the fact that if I have an algebra over this operad, there's only one way to multiply some number of elements. So if I take n elements and I'm applying this quote-unquote operation, then that means that there's only one way to multiply them. So no matter which order I try to do the multiplication in, right, there's only one way to multiply. That means that it's commutative. So this is the commutative operad. It's just a single point. It's just saying I have some algebra, and whenever I take some number of elements, this is my space of operations. There's only one way to multiply them. So the second simplest operad would be Sn. Well, really, so for operads, you know, there's like a one for each n. So when I take n elements, this is these are the set of operations I have for those n elements. So this is saying there's only one way to multiply them. When I have n elements here, it's saying that there's n factorial ways to multiply them. I can give you any permutation. So this represents an associative algebra. Because if I have an algebra over this operad, it says, okay, give me a permutation of the elements, then the bracketing doesn't matter. All I need to know is what's the order of the elements, and then I can multiply them. What's your question, Rex? Only multiply? Well, yeah, but it's like sort of like an abstract notion of multiply. So, yeah, you can always look at things in like certain categories and other types of operations, so you might be able to finagle it. So multiply here is like a quote-unquote multiply. I mean, it just has to satisfy like the axioms of being an algebra over an operad, and then we can call it multiplication, even if it's not like any sort of normal notion of multiplication. Just like in groups, right? We talk about multiplying elements of a group, but it doesn't necessarily need to be like arithmetic multiplication, right? So yeah, these are like your two simplest operads. Basically, this is saying like for any n elements, there's only one way to multiply them. This is saying for any n elements, I can give you an ordering of them, and then once you give me the ordering, then there's only one way to multiply them. So that would be like, if we're talking about n equals 3, there's basically 6 different ways I can multiply in an associative algebra when you give me 3 elements. So if I have 3 elements, A tensor, B tensor, C, I can apply some permutation of them in S3. Right, like maybe I switch the order to backwards. And then if it's an associative algebra, then I can just multiply them and I get the product of C times B times A. Right, and here at this step, I can apply any permutation I want, right? So the permutations are parametrizing the different ways I can multiply 3 things. I can apply some permutation, and if it's an associative algebra that's not commutative, I might get different results here depending on the permutation, right? Okay, so these are kind of your simplest notions of operads, but then, of course, mathematicians love to make things even more complicated. So there's also a notion of having a set of operations, but the set of operations here is somehow, in some sense, discrete, but there's a way to like upgrade it so that you have a space of operations. Instead of it being some discrete space, there can be some sort of like notion of a topological relationship between the operations, which, that's probably a lot to like wrap your head around if you haven't thought of that before, but because, normally when we do algebra, we think of our set of operations in this discrete sense. Like there's only one way to multiply things, or there's some, set of permutations that allow me to multiply things, but you never really think of algebras where the set of operations themselves have some sort of topology or some sort of spatial structure. But that's essentially what we need to deal with to answer this question, because here we're dealing with topological information here. So we're going to need some sort of notion of an algebra that takes into account that topological information and can still translate it, well, maybe not back and forth because we sort of lose too much information here if we're dealing with the integers, but we're going to need to deal with some sort of homotopical notion of operad here that acts on this space, and that's going to be, just like the Massey products give you information in the case of when the ring is the rational numbers or the real numbers. When you're working with the integers, the correct notion is a certain E infinity structure, which is a certain operatic structure that has non-trivial, like it's not a discrete space, basically. So we need to upgrade this notion of operad to, instead of our operations having discrete operations, there's some sort of relationship between the operations, like a literal spatial relationship between them. Okay, so are there any questions? I haven't defined operad, but here you can, like, even without me defining it, it's sort of, intuitive what I'm talking about, right? When I say this set is parametrizing the operation. So given one of the elements in this set, I get some sort of notion of multiplication. Oh, okay, yeah. All right, I'll let the ads go for a second, but right. So yeah, we have these spaces. So what could be a space of operations? In math, we like to think of, okay, we have all of these permutations of different ways to multiply. Could I create a space that is sort of like, in some sense, keeping track of the relationships? Like, can I create a space filled with triangles that relate all of these different permutations? Like, for instance, the simplest case would be you just have two permutations connected by a line. So let's just say we have two different ways to multiply two things. So we have like 1, 2 and 2, 1. So I can multiply things like a times b or b times a if I have an associative algebra. And then this line, like, sort of, so now I have a space, but the space is made up of, I have 2 points, so two different operations, but there's like a connection between them. So there's like a literal spatial line that connects the two permutations. Of course, we're not dealing with like an actual line, we're just dealing with like simplicial sets, but you can always take like a geometric realization and then you'll literally have like triangles and lines connecting permutations. Are we back from the ad yet? Yeah, it wouldn't even let me lower the length of the ads either without like lowering the cut, so I just left it where it was. But yeah, so what I was saying was we have this discrete set of operations here. This is just a point. This is like a discrete set of points, one for each permutation. But we can sort of upgrade this notion of operad to where the operations now have spatial relationships between each other. For instance, like a very simple homotopy in this, if we upgrade this space, a simple homotopy could be like between the permutations 1, 2. So we have 2 points, the permutation 1, 2 and the permutation 2, 1. And then there's also a line that like physically connects them in like space. And this line is part of the structure. So it's keeping track of the fact that 1, 2 and 2, 1 are related. So they might not give the exact same multiplication, but there's some sort of higher homotopy in the algebra that keeps track of the difference between these two. So there's actually you take the differential of this line and you get the difference between 2, 1 and 1, 2. So yeah. So basically you want to upgrade this structure because you want this E infinity algebra structure, which is this commutativity up to homotopy, and this thing is not commutative, but we want to add in all the homotopies that make it, that sort of fix this, which is basically saying we want to add in all these lines, and then we also want to add in like triangles, like there'll be a triangle between 1, 2, 3, 2, 1, 3, and 3, 1, 2 or something, right? So this would represent like a literal two-dimensional triangle, which is a homotopy, which is a two-dimensional homotopy between all of these permutations. And so essentially we can build up this higher space with permutations where we add in all these higher triangles where we relate all of the permutations to each other, and we can build this giant space, and they call this the Operads. I'll write this again in a second. Operads operad. I'll just call it BE. So this is like the BE operad. And so this is essentially we take like the bar construction on Sn. So we take all the permutations, but then we add in all like triangles that relate all the permutations, and like 3-dimensional triangles that relate 4 different permutations, and there'll be 4-dimensional triangles and 5-dimensional triangles and 6-dimensional triangles all the way up. And these higher dimensional triangles, this space is just relating all the permutations in essentially some way that up to homotopy, everything is just a point. Because like here you can see I can just contract 2, 1 down to 1, 2. I can squish this space and everything, I can just pull it down to a point. This triangle, I can squish everything down to 1, 2, 3. So yeah, this upgraded space is essentially up to homotopy is just a point, and that's something important. So let me just summarize that. So we have these discrete operads, commutative operad, associative algebra operad, but then we can also upgrade it to like a spatial notion, which is what we'll need to deal with this problem. So yeah, that upgraded notion is like a dg-algebras, so differential graded operad. Now instead of it being a discrete space of operations, you have your set of points of operations, but then you also have your homotopies between those points, and then you have two-dimensional homotopies between 3 points or whatever, 3-dimensional homotopies between 4 points, and so on. Right, so this BE operad, this is some sort of like, kind of want to think of it as like a brute force thing where like the set of permutations wasn't commutative, and it wasn't even commutative up to homotopy. So this thing is like we're just adding in all the homotopies that are missing. So BE is basically, you can think of it as the bar construction on Sn. I don't want to get into too formal what this means, but essentially you can think of it as like we filled in all the missing homotopies to make so that this thing that we just created is homotopic to a point. Because like I was saying, we took all our permutations, we added homotopies between them. Anytime I have 3 or more permutations, there's some 2-dimensional homotopy between those, etc. So basically we repaired all the discrete points and we added homotopies between them, so you could contract everything down to a point. That reminds me of the construction of classifying space. Yeah, classifying space is definitely related to this. Yeah, bar construction is totally related to that. Yeah. We think of G as a category. Yeah, there's a bar. I think there's a bar construction on a category too, or a groupoid maybe. I think for a discrete group, there's bar construction. I think you can also do it for a groupoid. Maybe there's a notion of for a general category. I can't remember. Yeah, I think this bar construction is very important. There is a lot of important generalizations where, so normally there's like bar construction for a group, bar construction for an algebra, but yeah, I think like Kyler is pointing out, there's also like a bar construction for a general, there's like a category notion too. So this is a very important higher category type notion, but I don't want to go into all the higher stuff. We can actually just deal with the simple case of just Sn. But this bar construction, all you're doing is you're adding in, it's basically just tuples of permutations. So like instead of having single permutations, you have elements like 1, 2, comma 2, 1. And if you take like the commutator of this with the differential, this is basically just, this is this picture, right? This is representing like a line between these 2 permutations. These are 2 individual points. And then we have tuples of permutations that represent the literal homotopy between them. So yeah, and then you can have 2 homotopies, like we can have 1, 2, comma 2, 1, comma 1, 2. This is a triangle that sort of relates like swapping things and then swapping them again, right? So this is like a homotopy between homotopies. 1, 2, to 2, 1, and then back to 1, 2. And we have all of these tuples of permutations. That's basically this bar construction. And you can show that if you have an appropriate notion of differential on this, that the homotopy type is just a point. So what's the question? Why was 1, 2, 3 triangle and not a hexagon? So everything we're doing with the bar construction, these are all triangles. So if I have 2 things here, it's a line, which is like a 1-dimensional triangle. This is a 2-dimensional triangle. If I put 4 things, it would be a 3-dimensional triangle, which is like a tetrahedron. Yeah, this is just a general homotopy theory construction. We're dealing with simplicial sets, and this is a simplicial construction. So everything is just triangles. Okay, so yeah, this so essentially the story is to deal with the lack of commutativity of this algebra. We need to upgrade our commutative operad to a GG version of it, which is like a homotopy coherent version of the point. So instead of just having this point, we need this bigger space, and once we have this bigger space and we have the algebra structure of this, then we sort of have like all of the homotopy information. So then we're not losing, then we basically have all the information that we need to construct that complex that I was talking about before, which is computing this, configuration space homology. Okay. So I can slow down for a second. Is there any questions? So we're looking at different types of operations on algebras. We're giving like a spatial structure to those operations, and yeah, these types of things naturally show up in algebraic topology because we're sort of blending algebra and topology together, right? So I guess this sort of is a natural operation that you would think of. This is literally blending. It's taking your algebraic symbols that are representing operations and it's giving them some sort of spatial structure. And the spatial structure is important for studying spaces. Yeah. It's coincidental that the triangle has 3 points and the permutation was on 3 numbers. Yeah, that's completely coincidental. Yeah. It could be like over here. See, we can just do like 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1. Like this is a 5-dimensional triangle which just relates 1, 2 to itself a bunch of times. Yeah, so that would be like some 5-dimensional triangle in this BE operad. Okay. Right. Let's see. So yeah, let's go to this other paper. So I think I put it in there a while back, but maybe it's way far back. So here's the second paper. I just put it in the chat. This one's like half in French, so I think there is a better version of this one somewhere, but the English version isn't too great. I think the French version is actually better, but I can't find a good translation, so oh well. And I don't speak French, so it's a problem. But luckily, most of the math you can kind of like figure out what it's saying. Oh yeah, Kyler speaks French, right? Yeah, French is the way better version. No, it really is. Like you can tell they're different. Like the French one actually has more stuff in it. But yeah, the name of the paper is Une decomposition. That's probably like French or Spanish pronunciation. A decomposition, a prismatic decomposition of the operad de Brat-Eklis. And this is Berger and Fresset. I personally think Fresset is probably one of the best living mathematicians. I think he's still living. He's getting old though. Right, so basically there's this BE operad, which is very easy to understand, which I just explained to you is basically just tuples of permutations. And so it had previously been shown that this cochain algebra, there was this other operad which was called surjections. And this acted on cochains naturally. So this acts on C star N MR. Ignore, I mean, naturally, I'm not using it in like a category theory sense. I think it's just that I think maybe it does have some sort of category theory, but I'm saying naturally in the sense that there's just like some obvious action by this other operad called the surjections operad. And in this paper, actually, I don't think they first define it, but they go into it more in this paper, which is there's this operatic map, which is called table reduction. And table reduction, it's important here that table reduction is a map of operads. Meaning, like, you have a map of linear algebra spaces, right? It needs to preserve the linear structure. So this is a similar thing. You have a map of the two sets, but it needs to preserve the operatic structure. So there's a notion of like composing elements together, and there's all this operatic axioms I don't want to really write down. But this table reduction map needs to preserve all of those basically. Or it doesn't need to, but to be an operatic map, it needs to preserve those. And it's a similar story in algebra case. If you have a map between two algebras and you have like a module over the first algebra, you can map all the elements to the second algebra, and now you can view it as a module over the second algebra. So the same story here applies. We have BE, we have an operatic map, and so in order to have an action on here, I can just apply everything to surjections and then have them apply on here, and now I have an action of BE acting on here. And the reason we want this is that this is known, obviously, it's constructed in a way so that this is an obvious E infinity algebra. Right, the fact that we basically filled in all the homotopies, connected all the permutations, and now everything's homotopic, we can contract everything to a point. That makes it an E infinity algebra. And so this is very important, the fact that we have an E infinity algebra acting on this space through this table reduction map. And this is how you get an E infinity structure on cochains. And once you have an E infinity algebra structure, then we know that up to homotopy, up to cohomology, everything is commutative. And so that, I mean, this isn't how they proved it, right? It was actually the other way around, but it is true that this algebra isn't commutative, but it's commutative up to homotopy, and that is implied by the fact that we have an E infinity algebra structure on it. And you can also show that surjections are also an E infinity operad. So we have one space of operations, we have another space of operations, and Fresset is showing that this map is somehow I'm not sure exactly how he defines this, but it's like, it's literally like a prismatic decomposition. So all these surjections, there's actually a map backwards, which he shows. I don't want to go into that too much, but this is called table completion, where it's basically a contraction of these two spaces. So this is basically just a projection onto here, and you can go backwards, and there's some sort of like way to view these as prisms in BE. Like, so surjections can be viewed as prisms in this space, and that's what he's talking about with this prismatic decomposition. Right. I want to write down like how the surjections act on here, but I feel like it's probably going to waste a lot of time writing down all the formal stuff, and I'm not sure like how much anybody is really going to get out of that, but let me see something. Hold on, let me think. Where I want to go from here. Are there any questions? So why am I supposed to be okay with permutations to be repeated just because they're not repeated next to each other? Geometrically, it feels like the triangle is the same. Yeah, that's a good question. That's a very good question. So you're actually, I guess the way you want to think of it is you're creating these triangles. Actually, yeah, it's kind of hard to view like the ones that repeat. I've had the same thought, like 1 2 2 1 1 2. It seems like it's a triangle that's sort of like squished onto itself, right? Like if we tried to draw it, it would be like 1 2 2 1, but then it like goes back to the same point. So it's a two-dimensional triangle, but it looks degenerate, right? So yeah, I've definitely thought about this. You sort of have to convince yourself that somehow it's not degenerate unless the 2 points repeat. So if you have like 1 2 1 2 and then 2 1, because you're not going anywhere after the first point, yeah, it's not obvious at all. But yeah, you sort of have to sit down with all the definitions and convince yourself that like something like 1 2 2 1 and 1 2 is still allowed as a triangle, even though it's like it looks like it's a degenerate triangle, but it's actually, if you look at the definition of what degenerate simplices are, it's not technically degenerate unless they're repeated in a row. But yeah, I agree that this is definitely a confusing point for sure. Okay. Yeah, it's a quote-unquote triangle. It's like a triangle in oh, maybe it could be like a triangle in like on a sphere, right? You can have triangles on a sphere that have 2 sides, right? Isn't that possible? I don't know. Yeah, it just still seems odd. But I think you just need to sit down and like convince yourself that it still makes sense. Yeah, spherical triangles. I'm trying to think if you can have like a 2-sided triangle, if that still makes sense. I mean, there's still yeah. I guess it is basically like a 2-sided triangle. Yeah, I guess you think of it as like it's like a triangle, but we squished these 2 points together, but there's still a non-trivial like 2-dimensional area there, right? This is exactly the degenerate triangle from my probability question a few days ago. Yeah, so I think this is actually no. Yeah, that's exactly what it is actually. So it's a triangle, 1 2 2 1 1 2, but now we've identified these 2 points together. So this actually squishes down to a point, and you still have this 2-dimensional area here. So it's still non-degenerate. You still have a non-trivial 2-dimensional triangle. It's just that we squished these 2 points. So yeah, you're actually getting like a circle, sort of like a, yeah. But that you still have this like space in between. I believe, yeah. So I think it still makes sense. It's just a triangle where, yeah. But if you squish 2 of the points that are the same together, then it becomes degenerate. You just have to kind of work through all the annoying definitions for simplicial sets and the differential and all that. Right. So let me go back to the original problem. So where is this all coming from? Where is it all going? Right, so for configuration spaces, so let me just start with really small spaces. So let's say we have 3 points. So let's say this is our graph G, and we'll label the edges, or I mean the vertices. And right, so for this, there's basically this giant graph complex that Professor Baranowski's talking about in the first paper I was showing you. It ends up that you get this complex, so however number of points you have, you're going to have that many tensor powers. So it'll be like a tensor to the third. There's going to be a map a tensor squared and a map to a. And there's actually many different maps here based on which 2 points we're sort of quote unquote multiplying together. So you can look at all the subtrees of this graph. In this case, there's like, there's this subtree. There's, well, actually, let's just look at let's first look at all the subtrees of size 1. So for every way to contract the edges, you're basically going to get a map here, which is multiplication of the algebra. So if A is the algebra, so you notice how like the number of elements we have goes down each time by 1. It's because we're going to be multiplying elements together. So if A is commutative, then when you multiply 2 things here in a certain order and you do the multiplication again, you don't get a problem in the end. So let's see why that's the case if it's commutative. So I'm going to take this subgraph. Oh, I want it to look like this, but whatever. Yeah, let's just look at it this way. Right, so when I do the first multiplication, so let's view all the elements as like A, B, and C. So you can think of this as like some element in A tensor power 3. It's just I take 3 elements from the algebra, and this first map, I'm going to get 2 different differentials based on whether I contract this first edge or this second edge first. And then once I do the first multiplication, I'm going to have another multiplication here to get to here, and it's supposed to cancel out. So we want the d squared is 0. Every time we go here, it's another application of d, and we want d squared equals 0. This tells us that this is the key to algebraic topology, really, is that if you have a chain complex and d squared equals 0, then it in some sense is representing a spatial structure. So you can take cohomology and you get some sort of spatial information. But in order for d squared to be 0, you need this commutativity, because essentially if you contract the edges in one order, it needs to be the same no matter which way you contract it. So if I do 1, 2 first, for instance, this will map to A times B, tensor C. And then if I contract the last edge separately, then I'm going to get A times B times C. So this is collapse 1, 2 first. And then this is collapse 3 into 1, 2, I guess. Right, so then in the end we get ABC, and in order for d squared to be 0 on the differential, the ordering shouldn't matter. So if I collapse 3 into 1 first and then 2 into 1 after, I should get the same thing. But if it's not commutative, we don't get the same thing. Yeah, so associativity here is not enough, because so if I do the collapse in one order, I get ABC, right? If I collapse 2 into 1 first, and then I do this collapse second, I get A times B times C. But if I do it in the other order, I get 3 collapsing into 1 first, so I get A tensor sorry. I get A times C, tensor B, and then once I collapse 2 into 1, I get A times C times B. So this is not equal to this usually, unless your algebra is commutative, right? So yeah, associativity of A is not enough to get d squared equals 0. But if you have this E infinity structure, then we can repair the difference between these, and we can add an extra differential term, which will help us get d squared equals 0, unless we need to add another correction term and another one, and there's actually like an infinite series of corrections, but of course everything's finite if some restrictions are made. But so yeah, even dealing with 3 points, a graph with 3 points, we already run into an issue of if A is not commutative, then you have a problem with doing these edge collapses in different orders. You get different products, and then if you take the difference of these, you don't get 0, so d squared is not 0. So you can see kind of what's going on here is you're multiplying things into the first element A, but B and C got sort of switched in their ordering. In the first edge collapse order, C came last, but in the other edge collapse order where we collapse 3 into 1 first, then C actually shows up before B. And that's a problem if we want d squared to be 0 and we want this complex to actually compute something that's like spatially makes sense, then we need d squared equals 0, and we can't have these being different. They have to be exactly equal so that when we take their difference in this differential, it becomes 0. All right, so we basically, we need some higher operation, some higher E infinity operation that corrects for this difference, and so then once we take another differential, it will correct this and we'll get 0. Right. So yeah, let's look at, okay, I see. Yeah, so let's just stick with this example. I think the 3 points example is like, it's very illustrative because you already have this non-commutativity even with this small case, and it's kind of much easier to write everything out with just 3 points. Once you get 4 or 5 points, it starts getting much more confusing. Yeah, even with the graph with 3 points too, there's like so many subtrees. So, well, maybe not so much with 3, but you could even imagine like a graph with 4 points. You're already getting like an enormous amount of subtrees if there's a lot of connection between the points. So one of the problems with this problem in general is that it's very hard to compute things, like even at least by hand. I mean, with a computer it's a little more doable, but even with a computer I'm having trouble computing stuff that's like 10, 11 points, because you just have like, there's just so many subgraphs, so many, so much permutations. But the computer can do it up to like, I think like 8, 9, 10 points is kind of like the limit. At least I have it written in Python. I'm sure it could be like upgraded in C and probably run a lot faster, but there's definitely like an exponential explosion somewhere. It might even be like super exponential. So it definitely explodes like at 10 or 11 points, where it's just like, after that it's not really doable even on the computer. But yeah, so this Bendersky, let's even go back a little bit further. So before we get to tensor products, this Bendersky Gittler complex, this is the original one that's computing what we want from the information in the graph. And this one doesn't have tensor products. It has Cartesian products. So there's actually instead of like before we had tensor products for the algebra, this is like m times m times m, Cartesian product. So this maps to 2 copies. maps to one copy. This is the differential, or one of the differentials, because it's actually a double complex. And when I say double complex, I just mean that each one of these individually has a differential that maps like within itself. So we could call that like script D or something. And then there's also a sideways differential that maps between these complexes. And so the total differential is like you take the plus or minus sum of these two. And this becomes like a total differential on the entire complex. There's like two gradings, and I think you add the gradings together to get a total grading, and then you have like a total complex with this differential. So yeah, this is the original complex, and then remember we had essentially the same thing, but these were tensor products, so it was like this tensor itself 3 times instead of having Cartesian product inside. And so here there's actually no issue with the commutativity, because we're no longer doing the product in the algebra itself. We're actually just using these pullback of the diagonal maps, right? Like you take a simplex, you send it to sigma comma sigma. And that kind of operation is commutative, right? Because if you're just copying sigma to 2 places and I do that again, well, now I just have 3 sigmas, and it doesn't really matter the order in which I copied them. I just have 3 sigmas no matter what, and as long as they're in the right positions, then so d squared is automatically 0 here, and I don't need to worry about any sort of problems like we were getting with this graph collapsing the edges in the wrong order. So if you do the same thing with this graph here, you already get d squared equals 0. There's no need for a correction term. The problem is like these complexes are gigantic, and I think the size of these spaces blows up. So trying to compute anything with these just becomes more and more unmanageable the higher number of points you have in the graph. So essentially what we want to do is we want to use the, we know from algebraic topology that if you have a Cartesian product here, there's a quasi-isomorphism between the cochains on a Cartesian product, and you can send it to the tensor product, and they have the same cohomology. So again, we have this notion of quasi-isomorphism where they're not exactly the same spaces, but if you drop down to cohomology, then you do get an isomorphism. So essentially, we want to take these giant spaces and map them down using the Alexander-Whitney map to get tensor products of these C star m's, so basically tensor products of these. But like I said, once we do that, then we lose the commutativity and we lose d squared equals 0. So the real key here is how do we lose the commutativity and then correct for not having it anymore, essentially. So we're going to map down to much smaller complexes where we take tensor products of these, and we're going to lose d squared equals 0, and then we're going to ask, okay, so now what do I have to add into the differential to correct for everything I just messed up? And that is essentially these E infinity operations that I've been talking about. Oh, I thought there was a message there. Right, so let me just rewrite what I just said. So here d squared is 0, this is good. But it's bad because we can't do any computations with this space. So this thing would actually compute what we want. It's just so enormously huge that it's almost impossible to work with, except for like some special cases where the simplicial set is small enough and the graph has few enough points and there's like few enough edges or something. Then maybe you could compute this using a computer, but it becomes more and more unwieldy as you get to like 4, 5, 6, etc. And if the simplicial set has higher dimension, then you're just more and more in trouble. So what we want to do is we want to take the same complex, but instead of Cartesian products, we want tensor products. And we know that these spaces are up to homotopy the same but we need to add in correction terms if we're going to be computing this d squared equals 0 again. So essentially we want to map this all. So map this double complex to basically the picture that I had written before, where A is just this guy here, and it'll just be A tensor A, mapping to A tensor A, two different maps, mapping to A. So here we have M times M times M. Here we have A tensor A, where A is just a single copy of M. And we shrink everything down to the smaller complex. All the other maps stay the same, but we get these extra correction terms for the fact that d squared is no longer going to be 0 once we do this. We have to add in all the correction terms. Once we get those, then now d squared is 0 again. And like I was saying, basically the correction terms are the fact that it's no longer, the fact that A is not commutative as an algebra. But this process of taking diagonals is commutative, but we've dropped down to this other complex where it doesn't work out nicely anymore. Yeah, so let me, just for the rest of the time, let me try to show you how to compute one of these correction terms for this particular graph. So the one we were doing before. This is kind of like your first non-trivial example of a graph where you're going to end up with some sort of non-commutativity correction terms. Because like we showed before, you get A times B times C, one direction of collapse, and you get A times C times B, and these just don't have to be equal to each other because the algebra is not commutative. So yeah, let's just show that the first correction term is like actually what we would expect it to be, which is this surjection operation. Yeah, that corrects for, so we got one, we basically had A times B times C one direction, and we had A times C times B in the other direction. So we need some sort of operation that fixes, this is, you can think of this operation as like 1, 2, 3, and this operation as 1, 3, 2. And so we need an operation that's like 1, 2, 3, 2, which is a homotopy between 1, 2, 3 and 1, 3, 2. And yeah, we'll show that this 1, 2, 3, 2 actually comes from the correction terms. So how do we decide what these correction terms should be? Well, if you have a certain projection onto a smaller complex and certain things are satisfied, then there's this lemma that you can use, which is the perturbation lemma, and that tells you exactly what the correction terms need to be. It's just a simple formula. So yeah, so let's talk about that for a second. So big complex, small complex, you'll probably hear me refer to them that way a bunch. I'll say like, this is the big complex made of Cartesian products, and this is the smaller complex, which is the projection using the Alexander-Whitney map. Or maybe the pullback of the Alexander-Whitney, or yeah. The blue. Right, so I don't want to go through exactly all of the formalities of why this is what you get from the perturbation lemma, but I do want to go through. You'll probably see while I'm doing the mechanics of it, like how this could arise from what I was just talking about with the graphs. So we're going to look at the same graph. So 1, 2, 3 like this. And I'm making the claim that for every subtree such as this one, there's going to be a higher differential term, which is a correction term. And this is actually going to map to that correction term, which we just wrote down before, which is this 1, 2, 3, 2. operation, and this is going to fix that problem we had before. So where does this differential come from? Well, it's the pullback of the map. Oops. So we're dealing with cohomology, but all of the cohomological maps are defined as pullbacks of maps on the homology. So I'm going to define everything on homology, and to get the cohomology stuff, you would just take the dual map. But so it's going to be, I'm putting the star on the bottom now, so this is a homology instead of cohomology. And we get a, so we have a delta map. This just copies sigma to sigma comma sigma. So this will be C star n m times m. And then in order to fix, normally we would map to we would use the Alexander-Whitney map to break the Cartesian product, but here we're going to fix the fact that we did that, and we're going to add in something called the Xi homotopy here. So H is Xi homotopy. And this is going to change degree by 1. So this is going to degree plus 1. So it'll be C star plus 1 n m times m r. Yeah, and then we're going to apply another delta map. We're going to end up in C star plus 1 n m times m. And then finally we apply the Alexander-Whitney map to get tensor products. So it'll be C, I'll just write star plus 1 out here. So it'll be, yeah, M tensor product with itself 3 times, yeah, M comma R. All right, and this is, if you compose all of these maps, that is the correction term that you get from, well, actually, it's only from one order of collapse, but yeah, this is one of the terms you would get from this edge. Sorry, I was missing the chat. What's the question? So, sorry, so every spanning tree of G gives a different small complex. Well, what I'm claiming is that every spanning tree of G, well, it doesn't even need to be a spanning tree, but any subtree of G gives a correction term, or possibly multiple terms, to the complex. And the way that you get them is similarly, you apply the delta, which comes from the edge contractions, you apply a homotopy, and then you apply another delta. And if you need a higher degree correction term, you're going to apply a delta, a Xi correction, another delta, another Xi correction, and then another delta, and then Alexander-Whitney. So yeah, and the larger the tree is, the more deltas there's going to be. So every time you're going to have n minus 1 deltas if you have n points. So here we have 3 points, so we have 2 deltas and 1 Xi, and you're going to have n minus 2 homotopies every time as well. So n minus 2 homotopies, n minus 1 deltas, but it's always going to be the same thing. It's going to be delta, Xi, delta, Xi, delta, Xi, delta, Xi, and then Alexander-Whitney at the end. And these are all of the correction terms have this the same similar form. So yeah, the only thing I haven't really defined here, I defined it a little bit explicitly for Stuckey in a private call, but the only thing I really haven't spelled out completely here is the Xi homotopy, which is a little bit of a mystery currently. Not for me, but I mean, I haven't explained it in the talk. But the delta maps are very simple, right? Because they just copy one simplex to some other position in the Cartesian product, and it doesn't do anything fancy. There's no like sum over some terms or anything. It's just a simple copying of the term. So really, the complicated stuff that happens is in this H. Because every time we do the delta, it's a pretty simple map. When we apply this H, there's a real lot going on with this H. So that will probably require a whole separate day to talk about it. But yeah, I could probably write down the definition, but Yeah. Let's just try to. Let's try to actually compute this, like I was saying before. So yeah, I guess we'll have to write down what this means to be able to compute this. But yeah, any questions? I know probably said a lot of stuff that most of you are a little confused about, but hopefully you're gleaming some insights about algebraic topology here and there every once in a while, hopefully. Right. Also, it might be important to point out that the degree of this map is in the total complex. It's always going to be changing degree by 1, because every time we change the size of the number of Cartesian products we have, we're actually changing the degree we're in. So we're adding an h, which is changing the degree, but we're also moving complexes, which is also lowering the degree. So every time we add an h, we're actually subtracting a degree as well. And in the end, you can show that in the total complex, this whole thing only has degree 1. Because it sort of looks like if we're adding multiple h's, like if we had more than just 3 points, seems like the degree might keep going up, but that's actually not the case. Okay, so what is this composition? Let's try to compute this. So the first map is just a delta map, so any simplex. Oh, I'm already killing the markers, wow. I only had this marker for like a week. So the first map sends sigma in C star n m r. This just gets sent to sigma comma sigma. Which is now a simplex in C star n m times m. Then here's the tricky part. Now we need to apply h to this. So sigma is a simplex. Let's say it's an n simplex, little n. So h of sigma comma sigma should be an n plus 1 simplex in the product space, right? Because this is a degree 1 map. You have an n simplex, so the thing I should get out in the n should be an n plus 1 simplex. So what n plus 1 simplex is this? Or, it could also be a sum over n plus 1 simplices, right? So some linear combination of n plus 1 simplices. Or I guess, to be more precise, I should say that. Linear combination of n plus 1 simplices. And how you compute this, so an n simplex is given by, I write out the points of the triangle essentially. Right, so there's always n plus 1 points. Sigma 0, 1, 2, all the way up through n. This is like, you have your higher dimensional triangle, and these are all the vertices in order. Right, so it's the same thing over here. Now we want to apply h to this. So this is going to spit out some linear combination of n plus 1 simplices. So what's the rule? Essentially, we sort of split this. So when we do the Alexander-Whitney map, remember we talk about like the first ith face and then the back n minus ith face. So we're going to do that, but on both of them. And for the first ith face, we're not going to do anything to it. And then for the last n minus ith face, we're actually going to apply the Alexander-Whitney map and then go backwards, using its one-sided inverse. So the Alexander-Whitney map is not a bijection, but it does have a one-sided inverse that goes the other way. Right. So essentially, the process to apply the homotopy is you split into ith face, the ith front face, and the n minus ith back face of the simplex. And then, like I said, for the ith face, you do nothing to it. You apply the identity map. And then for the other half, the n minus ith back face, you apply the Alexander-Whitney map, and then it's the one-sided inverse to go backwards. And the idea is that you're splitting your simplex into two things, and we're getting the homotopy between two maps, which is one thing we're doing nothing to it, which is the identity map, and the other one we're doing this composition of maps, which is Alexander-Whitney, and then go back. So coming from Cartesian products to tensor products, and then going back to Cartesian products. That's the composition that we're doing on the back half. I can't see a face there. Yeah. Yeah, you need to view. You can't see in n-dimensional space. I mean, if it's a triangle, right, then you can visualize it, right? Then you have your 0th point here, one first vertice, second vertice. And when I say split into ith face and n minus ith back face, you could think this could be like the first ith face to 1. This just being this homotopy here. So it's a one-dimensional face. And then the back face could be 1 to 2 here. This would be the back face. But that's just one splitting, right? You could also just split it into just 0 and then the whole triangle, or 0, 1, 2, and then just 2. So there's a bunch of different, I is an index, you're varying I. So there's a bunch of different splittings here. Okay, so first you split it into the ith face and the n minus ith face for both components. And in the first component, so front face gets identity map, aka you just do nothing to it. And then the back face gets a composition of Alexander-Whitney map and this, I'll call it the Eilenberg-McLean map, but it's basically it's the one-sided inverse. This is a composition here. EML composed with AW. And then finally you concatenate the two results together. So you did identity on the first ith face, you did this composition on the back n minus ith face, then you concatenate them together, and that's the map. Concatenation. So we call this the Xi homotopy, or sometimes we say it's the concatenation homotopy. There's actually two different ways to do this, right? Because you could apply the identity on the back face and apply the composition on the front face. So there's actually not a unique way to construct this homotopy. So I usually call this the left Xi, because that's meaning that we're doing the identity on the left half, but there's also a right Xi where you could do identity on the right half. And there's probably some higher homotopies that relate the two different Xis, and then higher homotopies that relate all the homotopies, just like we were discussing with the E infinity stuff. But yeah, so essentially, so we're doing this diagonal map. We get two copies of sigma. We apply H. It involves this splitting, doing something to the front face, doing something else to the back face, and then concatenating the two together to get an n+1 simplex, or a sum of them. Yeah, and then we apply one more delta map. But the thing is, with this map, the non-trivial stuff comes from when we collapse 1 into 3 first. So what that means is that it's going to change which type of delta maps we get. If we do 1 into 2 first or 1 into 3 first, it depends on which position we're copying the first component into, either the second or the third Cartesian factor. When you do the inverse, why don't you lose the extra degree that AW gave you? AW doesn't change degree. AW is a degree 0 map. So it's not a homotopy or anything. So delta doesn't change degree. The only thing changing degree is H and the fact that you're moving from one complex to the other. And in the total grading, each complex has 1 degree difference. So you're adding a degree only when you apply Xi, but every time, so actually, I guess, technically the delta map is changing degree. Because you're going from one complex to a different complex, and there's a total grading which takes that into account. So yeah, sorry, so H is changing degree, but the delta map is changing degree the other way. So every time you have an H and a delta, the degrees actually cancel. So you should have one more H than deltas, or no, sorry. You should have one more delta than H, and then in the end, it just changes degree by 1. What determines which bit copies where? Yeah, that's the information in the graph. So that's what I was saying here. So depending on which edge collapses first, basically you pick a subtree, and then you pick in order of collapsing the edges, and then once you pick an order of the edge collapses, then you get a particular set of deltas. So in this case, like if we collapsed 1 into 3 first, and then 1 into 2 second, then we would get delta. So this delta map is always the same, but then the next delta map copies 1 into 3. So I'll write that as like delta 1 comma 3. That's going to copy the first position into the third position. Because now once we've applied the Xi homotopy, they're no longer symmetric, so the first and the second aren't the same anymore. So when I copy the first into the third, I'm actually doing something non-trivial, since the first and the second aren't the same. Yeah. So yeah, let's do the whole map out. Well, I guess I can't really do it for, well, yeah, let me at least write it. So we have this sigma is going to delta of sigma. So we're copying sigma, then we're applying H of that. So this is H of delta sigma. And then we're copying delta 1 comma 3. So as, let me rewrite this all. Let me make this really explicit here. So given the graph, so every subtree is a sum over edge collapse orders. And for our example 1, 2, 3, I can collapse 1 into 3 first. So one particular collapse order is 3 collapses into 1 first, then it's just 1 and 2, and then 2 collapses into 1 after. So this is the first collapse, this is the second collapse. And for this particular collapse order, then the sequence of maps that we have to take the dual of is, so sigma gets mapped to sigma comma sigma. Then we map it to H, so H of sigma sigma. Then we apply delta 1 2 or 1 3, I mean. So we're gonna get how do I want to write this in notation? So this is gonna give us a sum over something comma something else, right? So I'll write it as like I'll just write H sigma 1 here. Just this is probably not formally correct, but so this is H sigma 1 comma H sigma 2 comma H sigma 1. Right, because Xi here, it breaks up the symmetry here. So the first component's no longer equal to the second component. So when we apply delta 1, 3, we're copying whatever that first component is to the third component. The second component is just whatever it is, and we just leave it the same. And then we take the Alexander-Whitney map, which projects this onto tensor products. So we get, a bunch of tensor product stuff, some sum over tensor products. So this is the composition, and this is changing degree by 1 because every time we apply a delta, we're shifting to another part of the total complex. That changes degree. Every time we apply an H, that also changes degree, but in the other way. So yeah, we always change degree by 1 because there's always one more delta than H's. Right, and so I guess I can probably show you the answer, but it's going to be a little bit hand wavy. But essentially what happens is at the first H, so yeah, what do we get after this output here? So what is this? That's really the question here, because then applying delta 1, 3 to the result is pretty trivial. We just copy it. And applying Alexander-Whitney is maybe not so trivial, but right, so what does sigma do to, or what does H do to sigma comma sigma? That's really the question. I'm almost not going to rush here, but I'm kind of running out of steam a little bit. But let's just look at how H affects. Let me leave this map. No, I got to erase this because I'm going to run out of room. Yeah, actually, let me just show you how H affects things, and then I'll probably have to stop there because I can probably write out like the full thing, but I'm gonna have to like skip over too much stuff. It's probably not gonna make much sense anyways. Let's just concentrate on what does the Xi homotopy do to sigma comma sigma. In other words, it's H of sigma of 0 comma 1 through n. So we're going to get a sum where I goes from 0 to n. I is basically where we're going to split, right? So it's going to be sigma what's the best way to write this out? Right. Yeah, I think I got it. Oh, and yeah, okay, so it's actually going to be a double sum. So the first sum is going to be caused by that first bullet point I had where we're splitting it on the ith face and the n minus ith face. So that's this I index here. But then in addition to that, we're also going to need another index for the Alexander-Whitney map because that also applies a split somewhere as well. So I'll call that like J. So that's going to go from I to N. Yeah. Actually, you know what? Since I didn't write this down formally beforehand, I don't want to write it down incorrectly. Let me give you like an informal definition, which is more like visual, I guess. So we have so we have sigma here, 0, 1, blah, 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 through n. Then we have another copy of it. And so essentially, what we were saying before is we're just going to slice off some front face of this up to I. And everything past I, we're going to split it off and we're going to apply Alexander-Whitney map, and then we're going to apply this map backwards, which kind of shuffles everything back into this Cartesian product. So we're going to get a bunch of terms, and in the end of the day, I don't want to write out the full sum, but essentially, let me just write out what the terms look like. So we're going to get a bunch of terms that look like something like sigma 0, 1, 2. Let's just say I is 2, so I stop at 2. Let's say it goes like 2, 2, 3, 3, 3. And now the other part of the Cartesian product is going to be, so it's going to be sigma 0, 1, 2 is going to be the same. That's going to, so that's where we applied the identity map. And then maybe here we had 2, 3 on the left side, and maybe we had 3, 4, 5 on the other side. So 3, 2, 3, 3, 4, 5. Wait, 3, 3, 4, 5. Yeah. Sorry, it's a little bit messy, but so this would be like one of the terms in the sum. We split the ith face at 0, 1, 2, so we have sigma 0, 1, 2, sigma 0, 1, 2. Those are the same for both of them. But then there was a 2, 3, 4, 5 here, and it got split into 2, 3, and got split into 3, 4, 5, and then we used repetitions to increase the degree to be the right size. So that's why we have 2, 3, 3, 3 here, and 3, 3, 4, 5. And every time there's a repetition in one of the sides, there's not a repetition on the other one. That ensures that in the product space, it's not a degenerate simplex. Yeah, so basically we get a bunch of terms like this. We go out to I, but this I varies. It's an index, so at first it's just 0, then it's 0, 1, then it's 0, 2, or 0, 1, 2, then 0, 1, 2, 3, and so on. And then there's another index where we split the second part and apply, Alexander Whitney, so the left half goes to the left side, the right half goes to here, and then we add these repetitions to beef up the degrees so that, it's not so that the degrees make sense, but obviously if the degrees didn't match, then the map wouldn't be well defined. It wouldn't be preserving degrees. So there is a necessity for this duplication of the numbers there. Okay, I'm extremely tired. That was a lot of talking, but yeah, I'm definitely willing to sit here longer if people have questions, but I think I'm pretty pooped mentally. Can't even think of the words. So yeah, I'll hang out here for a little longer, but that was my presentation, and I hope you guys liked it. I'm probably gonna continue talking about this next Saturday, so if you guys are interested in this and you want to talk more about it, you can always join the Discord, ask me questions there, or private message me if you want. And yeah, I'm hoping so the main goal of this whole thing is that we want a nice way to describe using operads and operatic operations what we get when we apply this perturbed differential and we apply all these correction terms, and all those composition of maps I was writing before, if we add in all those correction terms coming from those maps, what can we write those as operatic algebra operations? And it turns out the answer should be yes. We can use the surjection operations, and I came up with a formula that should give us the answer. We just have to prove that it's correct, basically. Thank you, Kyler. Thank you for showing up. I appreciate it. Anything else? So let me stop the recording here, but I'll keep streaming.